Okay, my name is Bastiaanssen. I'm a professor at the Delft University of Technology, and I am also the chairholder of UNESCO Global Water Accounting. And this lecture is about giving you an introduction to these topics of water productivity, which is very much an agricultural topic, and water accounting, where we look much more at river basin scale. So the scarcity of water is growing in the world. We get many more countries that are confronted by a growing water scarcity. And on this map, you see that Pakistan is one of these countries in South Asia. And today we will give some special attention to the situation in Pakistan. Now, if we talk about water management and especially about making water management more efficient, we have to really distinguish between the abstraction of water, or as it is called in this diagram, extraction, versus the consumption of water. And this picture shows you that what the situation is for three different water user sectors. And so you see that agriculture is taking a certain part of water, but that only, say, typically 70% is consumed. But the domestic sector and the industry sector is even much worse. So you see that only a small part of the water is consumed, which basically implies that a large part of the water is non-consumed and actually is recoverable for downstream users. And this is an important issue because if we want to solve problems in water management, we have to really look at how the water is consumed, because once it's consumed, it's not longer available to downstream users. And then if you look at this consumption in a bit more detail, you see that the amount of water for drinking and bathing is very small as compared to the amount of food that we, for the amount of water that we need for food production and also for environments. We all like to have green environments, but they take a huge amount of water, and this is not always very well understood. So if we have these river basins with scarce water resources, we should really look at saving in the category of big users. And this is really about food and environment. So in order to say something more in a quantitative sense about the value that we get from the consumption of water, we have introduced this concept of crop water productivity. It is something that has been invented by the International Water Management Institute in Sri Lanka, but also has offices in Pakistan. And the whole idea behind is that we maximize the benefits from this water consumption. So we get food and feed and fiber and energy as a consequence of water consumption. And very commonly it is expressed as the marketable crop yield. So we look at how many kilogram we can harvest per cubic meter of water, and that is known as this water productivity. And it is important because, again, it is an indication on how much water is really consumed. It's not longer available to downstream users. It's like a withdrawal of water from the river basin. And we want to see how much benefits and production we can get for that. And as you can see later on, there is a huge spatial variability of water productivity, and this indicates that it is really possible to produce more food per unit of water. So we can have very complex water management systems and irrigation systems, but in the end it's what we harvest and the amount of water that we consume, and that's exactly what water productivity indicates. So the upper part in our equation is the yield, the marketable crop yield, and we divide that by the amount of water consumed. And this definition is also supported now largely by FAO. There has been a very recent user consultation with experts all over the world, and one of the outcomes is that this is an agreed definition of water productivity. It's nice to see that this concept is also taken up by donors. More and more donor agencies also want to improve the water productivity in the execution of their projects. But there is one problem, and that is not easily measurable. In fact, there is not an instrument that you can put in the field and measure it. Otherwise, it would have been very easy for farmers because they could then look at the values, they can compare it with others, and then they can understand whether they are having productive on-farm practices or not. But there is a kind of a problem that there is no field instrument, and therefore I will show you in this lecture how satellite data can be used for that. Now, before I jump in the satellite technology, I show you here this diagram on the relationship between the yield and the actual evapotranspiration. And you can find farmers that have about 8,000 kilogram per hectare, and they only use 4,000 cubic meter per hectare, or 400 millimeter. There is a factor 10 difference between cubic meter per hectare and millimeter. And they do relatively very well. But you find also in this diagram, and all these dots are collected from literature. So it is based on an exhaustive literature review of the last 20 years. And you find also farmers that have only 2 ton of wheat, and they have 6,000 cubic meter per hectare. And that shows that there is tremendous scope for improvement. Now, this frequency distribution for rice, wheat, maize, and cotton basically show the same, but then it's expressed as a frequency distribution or histogram. And you find that the difference between the lowest values and the highest values can be a factor 10. That is kind of a number that you should keep in mind, and that there is a factor 10 difference, which basically means that you can really get much more production from a given amount of water. That's not only true for wheat, but it is certainly also shown here that this is applicable to cotton, maize, and rice. Now, the classical questions people ask me is, okay, but once you know your water productivity and once you are reminded that you are at the lower end of the spectrum, how can you improve that? And now, one of the things here in this diagram is that you can see that the water productivity is related to the yield, and that the very steep part where the water productivity quickly changes occurs at very low yield. So in other words, very low water productivities, like in this case lower than 1 kilogram per hectare, really is related to very poor yield, which means that it's the agronomic practice that is affecting the low water productivity. So it's not only an issue of water management, but it's also very much an issue of good agricultural practices, which shows the need for an integrated solution at farm level. Now, there are physical processes related to water productivity, and this diagram shows you the leaf at the left hand side in the green and the air in blue on the right hand side. And the connection between the leaf and the air is the stomate. The stomate is the chamber where water vaporizes, and the water vapor is taken out of the crop. At the same time, the carbon gets in, and the whole trick is to get a maximum amount of carbon and at a lower amount of water vapor. Now, this requires to better understand the water balance and the energy balance. And if we can solve these balances, yeah, then also we can say more about the water productivity. So before I continue with more examples, I would like to draw a few interim conclusions. So the first is that the agricultural sector is taking a lot of water, much more than the water needs for our domestic life. That also the water is becoming the scarce commodity, much more scarce than land. So it is common now to express the water production per unit of water. Um, it is really possible. We see from the wide variability that it is really possible to get more yield from the same drop of water. And that if we have really very low values, then it's more related to agronomy than to irrigation. So, as I said, it is difficult to measure in the field. There is no instrument, so we have to use some technologies to make an estimate. And in this picture, you can see two different examples. On the left-hand side, you see an energy balance model, or it is called here a radiation engine. The model is referred to as ET-look, and that is a method to compute the evapotranspiration and the production on the base of radiation. On the right hand side you see the aqua crop model from FAO, and that is much more based on the water balance. So in fact the transpiration of an irrigated soil or also rain-fed cropping system is computed, and then this is after normalization converted into a biomass production. Now, what is nice is that both systems have also been implemented in Pakistan, and that also the results are very common. So the level of complexity is quite diverging. The aqua crop is a typical field scale model, and it's quite complex. The good thing though is that it's a simulation model, so you can really study in advance on what is the impact of another nitrogen regime or an irrigation regime or a different type of soil treatment, and then you can immediately see what the impact is. The ET-look and also global WP are models that are more based on satellite measurements, and for this reason they can cover also much larger areas. Now, the ET-look model is having a strong physics, the physics that I have shown you on some slides before on this stomate. The global WP is a model developed by Sander Zwart, who has been one of my PhD students, who made some very acceptable simplifications, which then allows you to look at global scale. And I will show some first pictures on what the situation is at global level. Now, the energy balance is very much driven by the sun, by solar radiation, and in fact we calculate the heat fluxes into the soil and the heat flux into the atmosphere. And from that we can get a very good and reliable, overall 95% accuracy estimate of the ET, the evapotranspiration. Now, the typical energy balance looks like this. In figure 5 here you see how an energy balance looks like on a typical daily cycle. So the radiation is an Rn, the net radiation, and the majority, especially for irrigated crops, the majority of net radiation is converted into ET. Now you can also work it out in more physical laws and flow equations, which basically helps you to make an estimate for every pixel. Now, pixel can be 30 meter by 30 meter, or it can also be 100 meter by 100 meter. And using satellite measurements, you have a unique measurement of that particular area. So if you have a particular crop with a disease, or if you have some problems with salinity or something else, yeah, it is encapsulated into the measurement of the satellite. So it's really a measurement of the true situation on the ground. Now here is an example of the ET-look model for India and Pakistan, and yeah, what I really like about this is that you can even see the border between Pakistan and India. The values in the blue range, they are very high. They are 2 to 3 kilogram per cubic meter of water. This is for wheat. And the green and yellow part, that goes to the 1.5. Now, what is interesting here is that this is all the Indo-Gangetic plain. It is basically one agro-ecosystem. Historically, yeah, it was one country, yet after 50, 60 years of divide, you see tremendous differences in water productivity. In fact, you can draw the border of two countries on a water productivity map, which for me is very interesting. And it also shows that water governance is a big issue. Um, and apparently at India, this is stronger than in Pakistan. Now, one of the reasons for the difference could be climate. So we did a normalization for climate, but you can see that the Haryana in the Indian Punjab they still have much higher values. Now, instead of taking the water productivity, we used here the so-called WPS. Now, that is the water productivity score. It's just a normalization, like you have in the normalization for earthquakes on the scale of Richter. You also can have a scale of water productivity between 1 and 10. And another very interesting topic on such kind of map is that you can also identify areas that are really doing well. So even in Pakistan, you can see that areas in green are present, which means that certain systems are really managed well. And that is good to find out what the underlying reasons are that in certain parts of southeastern Punjab, the water productivity is much higher than, for instance, Sindh or in northwestern Punjab. Now, this then is the picture for the world, so it's averaged by country. And here you can see that certain countries are really doing much better than other countries. And the Egyptians are always very happy when they see this map because they come out as one of the most productive countries when it comes to the water productivity of wheat. And one argument is that not only the climate is just perfect, but it's also the soil and the big Nile Delta with all the fertile soils from Ethiopia that are not present in Libya or Tunisia. And that is one of the reasons for the lower water productivity over there. Now, I can provide you here with a few more statistics. This is an overview of the 10 major wheat growing countries in the world. Pakistan is, say, at number 10. And you can see that this water productivity, when it's normalized for the to the climate, ETO, is a kind of in the middle. If you rank by country worldwide, you see that Pakistan is a little bit to the left of the middle, so it's a little bit below average, but is a kind of acceptable, although locally there are big differences. The situation for rice is, however, much less bleak, is bleaker, sorry, because there the water productivity is really among the lowest. And if you look at the major countries growing rice, then you see that Pakistan is really coming at the lower end of the spectrum. In other words, they use a lot of water, but they get very little rice production back. Now, the explanations can be related to the physical conditions of the soil and the geology and so on, but also to the whole management. Now, of course, the irrigation and drainage management, but also the agricultural practices, they really should be revisited because they are really below average. So, the conclusion on this component of the water productivity is that when we look at the Indus Basin, then the wheat situation is close to the average, but for rice it's really below average. And one of the reasons is the lower yield of the basmati. But there are also a lot of other reasons why this is not so favorable. So Pakistan is typically one of those countries that really should embark on an international program to improve the water productivity, but that needs guidance and monitoring. Um, I guess the data that I show you in these lectures is among the first data sets for Pakistan. And we should explore this data set to learn from it and then repeat this kind of analysis maybe on a yearly scale or every few years to monitor the changes. Now, the water productivity is very important because water is crops are the biggest consumer. But to make an assessment on the total sustainability, you have to look at the river basin as a total. We all work on integrated water resources management. IWRM is on the education program for many years. But if we really want to look at the water used in agriculture in relation to other sectors, yeah, then we have to look at the basin scale. So the second part of my presentation here is related to the water accounting. And more information and background can be found on this website, wateraccounting.org, which is a multi-institutional platform that is supported by FAO, UNESCO IHE, and IMI. And I should say that the IMI, the International Water Management Institute, is the father of the whole concept of water accounting. It was in 1997, that David Malden of IMI has started to just to think about water accounting because it helps us to answer very specific questions that are related to allocation of water and management of water. And these decisions are very often made in consultation with lawyers and environmentalists and agronomists and water experts. And yeah, very easily you have a different understanding of the terms and the flows. So a kind of a standard accounting is really helping the whole negotiation process, but also to take away all kind of myths related to improving water management. So the system that I have developed is called Water Accounting Plus, and it's not only looking at the people who use water, but it's also looking at the hydrology and at catchments, and that is giving an opportunity then to also look at changes of land use. So if you just change your land use either by urbanization or deforestation or other forms of land use change, you can also study then the impact on the water availability. So the water accounting is a standard reporting, so it's a reporting system for water resources, and it's dealing also with the consumption and the services rendered from that consumption. And it is separating water also in the water that you can manage and cannot manage. There's a lot of natural flows that we people can hardly have control on. So we have to distinguish that better. We also have to find out which part of flows are already utilized and which are still utilizable. So it's like determination of the water flows in your river basin. And that helps us to understand these surfaces. So agriculture, of course, is very important, but also economy and all the other ones. Now, the financial accounting has been very successful. It was introduced more than 100 years ago, and there is now a kind of international standard for financial accounting. And basically, we would like to do the same thing with the water accounting. So we are developing 10 different sheets. And on every sheet, you can find one very specific topic of the water cycle. Now, of course, it's all related to the water balance and the conservation of mass. And this also helps us to get a better idea of the groundwater. Groundwater is the most difficult component, but if we know rainfall and evapotranspiration and flows in rivers, then somewhere also we will be able to account for groundwater. Now, to make the presentation easy for decision makers, we are developing sheets, and what you see here is a prototype sheet number 1. It gives you the overview of the resource, so how much rainfall there is, and how much water is depleted, and how much can be used, etc. This picture shows you that there is a gross inflow of 482 billion cubic meter. The unit is billion cubic meter, but we have a total depletion of 502 billion cubic meters. So somewhere there is more water consumed than we get from inflow. Now this difference is coming from storage, and that part in the left, the left corner, bottom left corner of this diagram shows you this delta S, the change in storage, which are more than 30 billion cubic meter in the Indus, and that's a very frightening situation. So since the data is very difficult to get for these huge and vast basins and also from different institutions, we like to take the data to the maximum extent from satellite measurements. And here, for those of you who have not worked with remote sensing before, this is the kind of information you typically can get. So you can get information on precipitation, but also on the biomass production, because that tells you something on the water productivity, and on the E and the T, whereas the E is the non-beneficial evaporation from soils, and the transpiration is related to the evaporation from canopies, which in general gives us benefits. Now, the remote sensor cannot solve everything, so we also explore global hydrology models that compute the water flows in more detail. And also these models, they become more and more robust. And in fact, this diagram shows you the nice agreement. On the left-hand side, a picture of evapotranspiration, or ET, from remote sensing, and on the right-hand side, you see the same picture from the hydrological model. And you can see that they're very similar. And the whole idea here is that you take the images first and you train the hydrological model. Now, if you have the hydrological model, then also you can calculate how much groundwater is abstracted. And so here you can see the Indus Basin situation, and you see many areas with 300, 400, 500 millimeter of abstraction per year, but also even places that exceed 8 and 900. Now, abstraction is one thing, the recharge is another thing, and yeah, what you would like to have is that you have a situation where you have more recharge than abstraction, but unfortunately the Indus Basin is not having that situation, and you can see here that many net groundwater is used. Also, you can look at the portion of the water that comes from the aquifer and the other portion that comes from surface water. So if you do conjunctive use measurements, and if you want to manage your conjunctive use better, yeah, then this is one of the primary maps that you would like to have. Now, just to wrap up my lecture, see, on the one hand, we can make a water accounting of the current year with all the problems of overexploitation and massive groundwater pumping. But what is even more interesting is also to look at alternative solutions. Now, besides water flows, we also can find here how much water is withdrawn for the various sectors and the land and water productivity. Not only in the water productivity for crops, but also in totally for carbon and for carbon sequestration, so that yeah, we can also make the link to the Millennium Development Goals for carbon. So You can look at the current year, but also you can look at the future. And what is appealing is that you can define a number of scenarios with certain actions to see whether you can really save water in the Indus Basin. Very often you hear solutions related, for instance, to the lining of irrigation canals, but the irrigation efficiency in the Indus Basin is already more than 84 or 85%. So it's very difficult to improve that further. And the water that is lost from irrigation is very often recaptured in a natural way. So that is not a real water saving. So to have a more precise definition, you can define different actions, and then you can see how much water you can save. And now in this particular case, the scenario C had even an early land retirement in it. In the options. So the irrigated area could be reduced by 15%, which is not very popular in Pakistan, but either they have to save groundwater pumping or they have to bring land in retirement. There's basically no other option. Now, option or alternative B, scenario B, shows that indeed it is possible to save about 38 billion cubic meter of water. And then you get these new water accounts, and that are much more healthy, and the gross overexploitation is gone. But then you have to reduce your soil evaporation with mulching and with other techniques. Also the reduction of evaporation from irrigated land. Um, but to keep up with the production, you have to have to give also attention to more biomass production, and you can utilize a bit more flow. So the good thing is that if you can combine the water accounting with water productivity, not only you can look on how you can make the agricultural sector more healthy and productive, but also you can look at sustainability. And I think this Indus Basin is a fantastic case because you could have a very good water productivity, but if at the same time you have an aquifer depletion of more than 30 or 35 billion cubic meter per year, yeah, then you know for sure that it's not sustainable. And now this kind of frameworks um, help the decision makers on the way forward, and also to have a standard terminology on water management issues. Thank you, and bye bye.